It's definitely easier to do videos than live. So we were talking previously about SEH, structured acceptance handlers, how we can make use of SEH overwrite. One good reason why we may wish to do that is stat guard could be in place, the GS. So if something is compiled with GS, then we distracted here. I was just in there a moment ago. So if something is compiled with the GS switch, then the stat guard is in place. So traditional buffer overflow is then made impossible. If they are utilizing an SEH though, and if there's the right gadgets that are available, then we potentially could instead do an SEH overwrite, and then the stat guard does not apply to that. So that's one very good reason to make use of that. So one thing that we had dealt with last time was, and I guess I may have this open in a different, I reset it. We had used the Mona Python script previously, and of course there is a manual for that. How many of you used Mona before? So a few people. And one of these, Corey had mentioned last time he brought our attention to null bytes, right? What's wrong with null bytes? What is a null byte? Louder?
0, 0.
Why don't we like it?
Does it stop?
Why does it stop?
Because it's not an instruction. So, obviously, it doesn't know what to do. Or it would spin.
That's a good guess. Any other thoughts? Well, one reason why is it really depends on the function being used that's causing the vulnerability, and I guess maybe that in some cases that could be it. But I'm thinking specifically of stir copy. Stir copy, you terminate a string with a null byte, so it encounters the 0, 0. That means the string is done, so it stops copying at that location. So if we're using stir copy as our mechanism for the buffer overflow, then we encounter that and it just stops. It's done. What's a function, a vulnerable function that we could use that deals with raw bytes, or we don't need to be concerned with null bytes? Austin?
Some of the network ones
Memcopy doesn't, right? Could you say it again?
Maybe just the vanilla receive.
We'll talk more about finding bad bytes, bad characters, but just being aware that they exist is something that, you know, we for whatever reason, we don't necessarily need to know why the 0, 0 null byte is bad. We just know that it is bad. And so one thing you can do is the option CPB. So we can exclude known null bytes. 0 day 0A. We see those. One of them is return carriage. One of them is I forget what, but we often see them with when we're sending TCP packets. They'll terminate a line. The OD 0 day 0A, those are frequently used. And so those are known bad characters, and so we could just go ahead and exclude those, and so it'll find gadgets where these are not present, and it looks at it from the standpoint of let me go to Sublime, make it a little bit easier to, I didn't mean to copy all that. So if I have something like this isn't a null byte because it's going to be interpreted like that. So it looks at each of these to see if it falls into whatever exclusion criteria that we apply. In this case, we're excluding these specifically as null bytes. So if I were doing that inside of WinDbg, looks like I have it active here. So I'll just go ahead and go to WinDbg and so load it, the load, and maybe I should make the font size bigger. It may be helpful for some of you guys to get closer to the screen, FYI. So load PYKD, PY loads are Mona, and I don't know why it does is whenever I make it larger, it goes back to black, so I guess that's why let's check it now. Yeah, okay, there we go. So now I can access Mona, do the pi and then Mona, and then if we're doing SEH, and then just if we want to copy this, then we can exclude those. And so then we run it and regenerate it, and it makes it a little bit easier for us. I guess it was already open. So this is now free of the null bytes. We've talked about these before. These are, of course, going to be important with the rebase, the safe SEH, the ASLR. So lots of pops there. We also talked about using ESP. So we could add ESP4, we could add ESP8. So what if we didn't have pop-pop-ret for some reason, which is pretty common. But let's say hypothetically there's just a very limited range. And depending on, I don't know if we're doing it in this class or for some of the doctoral students, maybe doing it at a later time. Some of the bypass for stuff, it can get a little bit more complicated, but let's try this one out here. So I think this is more or less kind of where we left off. In class, there were some a couple issues that I just wasn't thinking clearly, but it was resolved. And so if we wanted to change that to something else and see how that worked, we could check that out. And I'm doing this just because of little Indianness. And there's a way so you don't have to do this, but I'm just doing it at this stage just to emphasize the idea of, little Indianness and hey, this is what's actually going on. We'll make this a little bit easier as we progress. So I could change that and comment it out, and then that would be the add ESP8. And we could see how that works. So go to our Sigwin, and of course I'm in a breakpoint here, so I hit G for go, and then we get an access violation. At this point I want to check my exception handler. And I see the NSEH down there at the bottom, in little endianness, so EB, jump, and then 06, 6, and then NOPS. And then right there is our SEH overwrite. So I'm going to do the U, which is a very convenient command that lets us see the disassembly that would result at that location. So we have add ESP60. I actually love that command so much. I actually integrated that into the reverse engineering tool that I created, the Jop Rocket. But in any case, so at this point, I would maybe set a breakpoint here. We can view our breakpoints with a simple BL. And so now I could hit go, and that would probably take us, it should take us to that spot, hopefully. We do get a breakpoint. That breakpoint has been hit. We can view and see what's going on there. So add ESP 60. That's not. Oh, let's switch this off to a different one. We were working in a different file, so let's. I executed the wrong one because I was experimenting with some other stuff. So let's go back to. View our EX chain. Let's grab the breakpoint there. Oh, that doesn't look correct there. So I put that at the wrong spot, obviously. Just one of those things where talking and narrating is a little bit different than actually doing it yourself. You can sometimes get distracted. So I had put that incorrectly at the NSEH, which should contain our instructions to jump over, and so I've now placed it at the correct location. So third time's a charm here. And I will make these files available to you guys on D2L, so if you wish to do some of this on your own, you can do so, although you may not feel that it's necessary. So now that takes me to add ESP8, and I'm viewing ESP here is pointer and symbol. Other ways you could view it, so you could also view it as long unsigned, or you could view it as long hex. So I could do ESP plus 8, and that says that location there. Let me try this again. So ESP 8, and then view that there. And so we see ESP plus 8 will then lead us to that location. So we can, just one way of verifying, this is actually what it's doing, how it's working. So we see that we have gotten to that location, and it'll do jump EB06. And so the way it presents us is it just goes and calculates the actual virtual address. So it would take us, we go 1, 2, 3, 4, 5, 6. Is that right? Yeah, it is correct. So then that would take us to that location. So we're jumping over that, and then what follows then, of course, is just a series of NOPs. So NOPs is no operation. And that's what the 90 is. So this is what you call, what's the term for this? Correct, NOP sled. Sometimes different heuristics can detect a NOP sled that consists of all 90s, so that may sometimes be ill-advised. So you could do something more benign, that like increment EAX, increment EBX, things that functionally may be like a NOP, but it's not going to have any ill effects. Of course, you also need to be cognizant of, and this is more true when you're going to return-oriented programming, if we're doing increment EAX, are we using EAX at that stage, does that need to be protected? If it's not, there's no need for it to be protected, then we wouldn't need to worry about that. Or it could be move EAX. Even if we needed to protect that, then it still would have no effect on it. So that's what we call a functional NOP. And then over here we get to our shellcode. So there's also an option, so we could do run to cursor. So I did run to cursor, and now we're at this location. We're about to start in here. And what do we think's going on right here with this code and the shellcode? Well, it's maybe easier for some of you than others. Loading the PAB is what one person said. Why is it loading the PAB? So FS register has the offset. Offset 30 leads to the PEB, so FS points to something called the TEB, or the TIB actually. If we look here at our offsets, which this is, I have a scratch pad open, so I'll unclose that. It's down here somewhere. And what's going on with the rest of this? Doesn't need to be the same person, although it could be the same person. So we established what was going on right here. Loading the PEB.
Could be loading API calls. Because it's going offsets of
It may lead to those at a later stage. This next one is loading a LDR structure. So essentially here we're walking the PEB, and then we get to the DLL base. So they're moving that into EAX, and so if I'm correct, oops, I meant to scroll up over here, EAX there. So that looks like 000, that looks like a base address of a module. So I could do LMF to load modules, and I could just manually inspect 738 in TDLL. So they've gone and they've loaded the base address of that. And some of the rest of here, what's going on with this code here? Doesn't need to be line by line, but big picture.
Is that where it would be loading the API call, but then into DLL? Like making, passing parameters in for some type of function call?
It's getting kind of to that point. So right there, it's let's see. Before we get to there, we have something going on with a pointer to EDI, and EDI is some value, which I haven't even checked this out yet, so I'm not sure. Okay. But in any case, EDI is checking for something, doing a comparison. If it's not that, then it goes back to this location. So I guess it's just probably just checking to see maybe if they were successful with NTDLL. I'm not sure. But what I do recognize right here is these are some of the offsets that are familiar to me. So these are things that are used to walk the PE file format. And then eventually we can then, like what Bailey said, try to find some function.
I think what I was thinking of using and most of them is that little, I think the function names are in NTDLL and it's comparing the 4 bytes for the function name, which is moving through or finds the right function to use. And all I did was use it off the offset. But maybe it's different from that.
Yeah, so he said it could be possibly going through and searching for the function name NTDLL. And you meant that at that location, or you meant that down here?
Yeah, I think those 4 bytes might be
These 4 bytes?
yeah.
Okay, good, because I didn't think you meant that over here at the top. So we could maybe do, well, let's go do a run to cursor right here. And let's see, do that one there and see what's in ESI. So it's not a valid memory location. So
Step one more, it'll add whatever's in the AX to it, so then it should be fine.
So it's inside the image port directory there. And then we're doing a comparison here. Like what Austin said, to maybe check and see so we could maybe go and try to that's not the right one. So looking for, and this is of course, and it shows that he's absolutely correct. So CRE, so probably create, is looking for that. And then it will do another comparison with another offset, possibly. But we don't need to be concerned with all the details here. This is a shellcode to load a calculator. I just wanted to touch on some of what was going on there with respect to loading the peb and trying to enumerate and then find. Eventually, it's going to find an address for a particular function. So it'll be create something, maybe create process, create whatever. Actually, I think create process is kernel 32. So. You guys will have an opportunity later on in the semester to write shell code. So some of this will come back to haunt you at that point. So I also wanted to take a look at another item here, another application that we can attack, and this is an FTP utility. So one thing that you would want to do here is to we go look at settings, and there's really not much there. It doesn't really give us a GUI. It's just something that we can set it up. It can be an FTP server, and we need to try to find a way to crash it. And there's one way to do it through SEH. So first step here is maybe figure out some of the commands that it would make use of. So you could do something like Wireshark, and you could go to capture interfaces and start, and actually, no, this is. So I connected to it. We saw some traffic there. That was the address for it. But we're not going to spend too much time on the vulnerability discovery aspect of it. Kind of give some of that away just because we're more focused on the SEH side of it. But right here, I'm trying to traverse structure. It says cannot find file there for whatever reason. I can go over here and let's see which one. So this one is 9. So I could do follow that stream. See, user logged in. User is current directory. And this is one of the commands that came over the line. There is, or where the wire is, CWD, and that's changed working directory. So over here we then see the offsets for that. So it's 435744. You know, if we're doing it in Python, we can just directly do CWD. And then to terminate it, we have 0D, 0A, which we referenced those earlier as those are some potential bad bytes. But that's how we conclude that. So if I were, if we're trying to fuzz an FTP application and we're doing it with Python, Python is our scripting language, then we need to see what it's doing, how it's doing it, so that we can replicate that in Python. And in this case, we're wanting to do that with this. So change working directory is going to be something that is going to be vulnerable for us. And don't need to click on that. It's blue. It's not that blue. This is something that some of you guys have worked with before, but this is just an in-class exercise, so obviously you don't have to do it again. But this is a function call that can potentially be vulnerable, and we can go and check this out. half the time it doesn't open when I click on them, so we'll see. So we create a path name from different components. We have our drive, directory, file name, extension. All of those come into play. We can read about those, learn about those. But we go down to the remarks, somewhere down here. Maybe not. We're on the wrong page. I guess I must be on. Well, there is one MSDN page where it does describe that this potentially can lead to a buffer overflow situation if we don't use the null byte. So make path could be a function that is vulnerable. Creates a buffer overflow system because if we were to we go to the CW, which all we're doing with CWD is we're just changing working directory. That's all we're doing. But if the input exceeds a certain amount, then that can cause an overflow. Now, if you're just doing this on, actual operating system, you're not going to run into that issue because Windows isn't going to allow you to have stuff, directories, and file extensions that are going to naturally exceed that amount. But if you provide those parameters through Python, through scripting, then you can, send whatever you want. So we'll see how we can do that here with Python. So in this activity, I talk about make path being vulnerable. We discuss some of the reasons why that's vulnerable. And so that's why we are interested in CWD. And if we actually go and open some of these up inside IDA Pro, we can see that it does use MakePath extensively, both in IDA Pro as well as in some of the various DLLs, and we may potentially do that. So I have a script here that we can use to kind of get us started. So there really is no shellcode there, it's just NOPs, but that's where our shellcode would be. That we need to have something. We need to have our a sufficient number of bytes to cause the overflow, and then from there we need to have an SEH and then SEH, and maybe some NOPs or some padding. And then leading to our shellcode. So some of this stuff here is really, it's all 90s NOPs, but you would fill this out and make it more specific. So I might instead, one thing about Python is I could go like this and do buffer equals, say, bad, and that will overwrite what was before it. So maybe I do bad equals A times 2000 just to start things off. Some of the mechanics here, this needs to be, for it just to work, username and password need to match what is set up inside the software. So I would want to, I have it set up so both of them are anonymous. And if you didn't do this, then I think this is pass. then that wouldn't work for you. What do we think we would do next at this point if what we're trying to fuzz and attack is the changing working directory? Look at the model of what you see there. So we're providing username, providing password, or is that password? So PWD, it looks like. So I probably would want to change that to PWD. What would be the next step?
Send the CWD command with a bunch of inputs.
Yes. So CWD, and we mentioned the plus OD5A. Or was it that? We'll see in a moment what it was. And actually, this doesn't actually matter that we include it, because we're going to put our, so we have CWD space, because notice that there's a space between them. And then we want to put our malicious input. In this case, it's bad, so we're just simply concatenating strings. And hopefully, unless there's some trivial error, this should then work for us. So let's go to WinDbg. And this one I do by executable at first, the first time I find it, which KMFTP. Because it's not always at the bottom unless you've crashed it and then you restart it. So I save it and we can hit our, am I in that directory? Yes, I am. And then we also provide address. Please log in with user and password. So it's accordingly, I'm not doing this. Oh, so PWD was probably print working directory. It's vaguely like password. So now I'm over here, I see the C string, and if I wanted to open that up, and this is part of, sometimes part of the process is, these are all things that we could go and investigate. This particular MFC42 is a DLL that's inside Windows, and inside Windows it's WIL64, because this is a 32-bit application, and since it's 32-bit, it's using the WIL64, which is the opposite of what you would think System32 is 64-bit. But that actually, this MFC42 DLL exceeds the capacity of IDA Educational, so you guys wouldn't be able to analyze that. I could also check out KMFTP, and then also see that some stack information may not be available. Some following frames may be wrong. So that could be maybe one location that I could look at. KMFTP plus 0x831. I meant to type a U in front of that. So we see some moving, some variables, load effective address, and then there's a call. So dword pointer, ESP, I don't know. But in any case, we can maybe return to some of that stuff. a bit later on. So there we see that we've occupied that region of memory with our 4 ones. So then we could start to improve upon that a little bit. So let's do it kind of like, sure, let's do it. This way we won't have to spend ages going over all this stuff. I hate it when it puts those little, tries to suggest what's next, and it doesn't allow me to use my arrow keys and forces me to use the mouse. So go ahead and close this out and try it again, and just relaunch the FTP and find it and attach. I don't have any breakpoints at this point. Operation completed successfully. So what does that tell us? It just means I need more. It didn't crash it. So I had 2,000 before, and then I went to this other. So I think that's what it means. Oh, absolutely, yeah. You're absolutely right. You guys gotta tell me that before I make the mistake. That's all just part of the exploit development process, and as you make stupid trivial mistakes, and rather than just showing you guys the code, I'd rather work through it slowly so that when it comes time for you to do your own, that everybody can accomplish it and not feel left behind. And there we go. Same error message as before. And then 4.5. So now I need to know what that is. So A, B, C, D, E. So somewhere in this vicinity. Actually, let's do it like this. Let's do Am I really that lucky, or did I not save it? Or am I mistaken and that's not E? Let's go check and see if that is. Yeah, that's an E. I just wonder if I didn't save it, but we'll find out, I guess, in a moment. So it did save it that time. So we're ready to launch it there. Now we got 6.5 and also we see the 6.4 there. So this should be our SEH there. So 6.5 is E. So I'm going to subtract. We have 4 there, and then 1 here, so there's 5 of them. So let's do 5, and then here this can be we'll have our SEH, or an SEH. And then our SEH, hopefully. Let's make these A and A. Really? Why am I messing up? Oh, okay. So that makes sense. So it's the other down here. So some of these things just have to think about them a little bit. So the last 3 of the D's, that's where we're going to start. So I'll just remove those. It's 10, so I'll subtract 3, make that 7, and then paste that there. And it looks like I lost our B. So we got a busy. It's gone. Up. So we have successfully occupied it there. So our next stage then is, what's the next stage? We gotta get our mono out. And then we want to do our pi because we're invoking Python. And then SEH, and then get that command that we had. So I don't have to type all that. We can go and find that location for us. And so what's going on when we see something like pop pop ret 0C? What's that mean? You know, there's only 2 or 3 people I could probably call in. How would you compensate for something like that? With ROP.
You have to put in some padding.
Yep.
Afterwards, just like some check and you wind up with it.
So what he was saying essentially is, so this is C. C means 12. So 12 you divide by 4, a D word, pointer, so 3. So there's 3 other addresses that you would need, that it would, or 3 D words on the stack that it would take off. So you would add padding for 3 D words. So that, because when it runs that, it'll automatically take off those extra 3 things. So some extra padding, some extra A's or B's. For SEH though, I wouldn't even worry about that or think about that. We would just want, but now maybe you know why you would not want to do that, just because you got those extra steps to take care of. So we want ones that are just normal, pop ret like that. We've already taken care of our null bytes, so we don't have to worry about that. So we could go check that out, and I could go over here, and I want to make sure that that's correct. So do my U, so I could see the disassembly that results at that location, and it's pop ret. We don't care about what happens after that, because we go to the ret, and so we don't ever hit any of this there. So we can use that. So we figured out our NSCH. Now we figured out our SCH. I'll just paste this here again, and doing it this way just so we can understand the little Indian. Make sure I don't lose my place there. So it reads it in this order, this one first, or this one first, then this one, then this one, then this one. So I'm just going to do double quotation and then comment it out and then Control V. So I've taken care of my SEH, and I have that there in case I made a mistake. I can fix it. And I'll show you an easier way to do that at a later point, so you don't have to mess with that. And then now we need to do our NSCH. So we'll just do what we did before. So the NX, we want to do the EB069090. So we should be good to go, hopefully, unless I made another error, which is very possible. Let's go up. Say that again? Exactly. And we can tell that because it has a different color. I guess actually that doesn't matter. So, but he was absolutely correct. We were missing out on that. I think it's already running, but it doesn't hurt to double check there. And that does look correct, I believe. Actually, it doesn't look correct, so I was wondering why this was screwy, but so this should be opposite little Indian. So I have this the way that it should be, and it should be like this. We'll just go ahead and see what happens. So take that here, set a breakpoint. Do BL, I can check my breakpoints. And G for go. So breakpoint hit there. And I'll step through this one at a time. So pop, ret, and I have, see, like I said, I did it incorrectly, so I have nop, and then it's interpreting the 06, and that's push ES, which is a register, and then EB45, that's jump. So instructions are variable length, meaning when we go at the opcodes, in this case, it could be 90 is a completed instruction, 90 is a completed instruction. This is a complete instruction. This is a complete instruction. So depending on where you start, things could result differently. So go ahead and fix that here. Let's set our breakpoint, or obviously I didn't set a breakpoint. G for go, we do our pop ret. And then now I have the EB06, which that is what we want there. So this actually is correct there. So that will then allow us to jump over 6 to, and where does it go? It'll go to 04, which is somewhere in the middle of this, and then with 6.5, they're just going to throw up an error there because that's not a valid instruction. So. And of course, we would expect that because now we've done that, we can create a NOP sled, and then we could create shellcode. So I have all this other stuff here. I could do something like bad, or actually I have so much. Let's maybe clean this up a little bit. So I could do, let's change this to an SEH, and we could do bad plus an SEH plus SEH plus NOP plus shellcode. And we can do, let's do some NOP of let's do 80 of them, just random, and then shellcode. We'll talk more about creating shellcode and all that at a later time. In this case, we'll just take this shellcode and see if it works, and probably will. Invalid syntax. Oh, it's down here. There we go. Looking at the wrong knob. So this here is the result of, it's probably not long enough, so we need to maybe add some more. Unless I made another, actually I'll probably just call it padding, but padding is triggers, sends a different message. Okay, so I'm sending bad, and that's why I need to send buffer, because we're changing things here. Go ahead and set our breakpoints. And G for go. And step through these. And I'm not sure where it took me. Don't think this is where we want to be here. May just be a shellcode issue here, but we're not going to spend any more time. Actually, let's think about this. Yeah, it's probably just a shellcode issue, but I don't want to belabor this too long. I'll make it too tedious for you guys. So what I will do here is, instead of this, let's do padding of 200. So I guess what I had meant to do but forgot to do is I mentioned this as being something that we might be interested in investigating. So if we're just trying to understand the nature of the vulnerability that caused it, and of course I've already bypassed it, so let's do that once again. So let's see if I can do a breakpoint here. And could not be resolved. Oh, of course not. Didn't do this correctly. There we go. So the breakpoint is indeed present there. So I hit that here, and I can look at the calls that led up to that. We could go inside MSV or the make path, and one of these, I think it's 14, is, let's actually take a look at that here. I don't like this one. Let's find a different one. I guess maybe this is the only one that there was. So we can see different arguments. So 1, 2, 3, 4, 5, 6 arguments. So we have full path of buffer, size of buffer, size of buffer in bytes. Drive contains the letter, directory path, file name, ext. So this is 5 and 6. And we can see some of these values here. And if you set the breakpoints right, you can see how they're loaded into there. But we could also just go and view some of the contents. And I think, let's check this one out. So it's making another call to make path here. So this would be the first argument, second argument, third argument, fourth argument, fifth argument, the file name, and then the extension. So I could go and maybe check that out. Oh, no. Just like I'll think that'll make a difference. Well, maybe relative to there's a certain place where you can look at it and you'll actually see all the A's in there. I think in this case, because we got inside make path and then we looked at it, so I should have maybe checked some of those parameters out before the original call to make path. But other things that we could investigate is trying to maybe investigate some of the initial vulnerability. Is we could go inside KMFTP MF path is directory, path add. So we're adding, and this all, if you think about it logically, CWD, this is our vulnerability here. We're changing working directory. So what I could do is I could go and find that CMFTP CM. So let's go file and then open file location. And it's a DLL. We can see that there. And this is below the threshold, so it's not too big. We can open this up. Is it not going? I must have clicked something. Oh, okay. So I have using iEducational inside the VM, which I guess I really shouldn't be doing, but I'm in the wrong VM, and so I have it installed in that VM. So we'll just go ahead and paste this out here and use my real. Did it? Oh shoot! It's doing the same thing it did last time, where it's getting stuck here. Those of you who were present last time, we had this whole big deal where I tried to copy a file outside of the VM, and then we got stuck there and had to restart everything. So and it happened to me again. So I'm not sure why it's doing this and why it's preventing me from copying this. But this is going to stay here until I close down Workstation and then have to probably restart it. So I don't know why it's starting to do this aberrant behavior, but I was going to open that up inside my actual version of VitaPro. We're going to investigate that, and I would just take you to that location, and you would then see the make path, and so nothing too special. Really, the vulnerability really lies at the heart of just the nature of, how make path works, and things not being properly sanitized. Again, the idea that if you don't have the null byte in there, then it's going to continue on. So typically when makepath is used, normally there will be a null byte, and so if we're doing things with Python scripting, and we can make it vastly exceed what it should be. Unfortunately, we won't be able to take a look at that because of VM issues. But do we have any questions? Anything people would like to add? Things that they thought maybe I left out? All right. Well, we will be having an assignment on SEH coming up, so something to look forward to. The purpose of today and last week is, again, just to kind of get some kind of hands-on familiarity with some of the process that goes into it. We kind of bypass some of the vulnerability discovery aspect of it, although we kind of slightly address some of that somewhat. That should likely be reflected in your guys' homework, where you will need to engage in a little bit of vulnerability discovery. So, all right, see you guys on Thursday.